Okay, now today we are going to solve one geometry problem which appears in the IMO shortlist in 2001. So from my point of view, this is a very easy problem. So let's take a look at it. In the problem, a square PQRS is in the interior of the triangle ABC, where PQ are on the side BC, R and S are on the side AC and AB respectively. So, as it shows in the diagram, we can know that, PQRS is actually a square. So, and also we denote the center of PQRS as A1. As you can see, the point A1, and then we connect the points A and A1. Then we get the line or the segment AA1. Similarly, we can get the lines BB1 and CC1. And what we want to prove finally is the lines AA1, BB1, and CC1 meet at one point. For this kind of question, for the three lines made at one point, we might think of using the converse of Seva theorem, right? Because that's one proper way to prove three lines made at one point. So actually, it is quite useful for solving this problem. So let's see. We cannot easily get the ratio of the segments. For example, if we extend the segment AA1 to let it intersect BC at one, maybe like point D. So what happens when what can we get from BD over DC? What can we get from that? We cannot get any or many useful information as we can. So actually getting the ratio of the sides of the segments is not a proper way. So we might think of the signs of the angles. Let me show you how to do it. Here, if I draw a triangle here, if I draw a triangle, and there are three lines meeting at one point, and we denote the angles as 1, 2, 3, 4, 5, and 6. Actually, this equation holds when the three lines meet at one point in a triangle. So it is sine angle 1, sine angle 1 over sine angle 2 times sine over sine angle 3 over sine angle 4 times sine angle 5 over sine angle 6 equals to 1. So when this equation holds, and that means the three lines meet at one point, this can be proved easily. So I will not prove this in this video. So after having the thought, what can we do to get these two angles? Maybe we denote them as angle 1 and angle 2. How can we get it? Or I can give you a hint. If we connect the points A1S and A1R. What can we get? Since A1 is the center of PQRS, so what is important is A1S equals to A1R, right? And also, we can easily know that as A1 and point Q are collinear. Not only this, but also R, A1, and P. That's very obvious. So we can also connect the points A1Q and A1P. So we know that SA1Q and PA1R are both lines. So this problem becomes easier because we want to have the signs of the angle 1 and angle 2, right? So how can we get it? Notice that we have one word that is sine. So what can we think of when it comes to the word sine? Maybe you can think of the law of sines, and that's the key of this problem. So the law of sines, that is in one certain triangle, maybe ABC. What can we get? We can get BC over sine angle A equals to AC over sine angle B equals to AB over sine angle C. That's the core, that's the key of the problem. So after having this, what can we have? Or in the triangle A as A1, we can have A1 S over sine angle 1 equals to A1 over sine angle ASA1, right? So what is angle ASA1? It equals to, like here, angle ASA1 equals to angle ASQ, right? And equals to angle B plus angle SQP. So what is angle SQP? It is actually 45 degrees, right? So it equals to angle B plus 45 degrees. So it equals to A1 over sine angle B plus 45 degrees. So that's the ratio of A1S over sine angle 1. Okay, and in the triangle AR A1, what can we have? We can have A1R over sine angle 2. It equals to AA1 over sine angle ARA1. So in the same way, we can get that the angle ARA1, actually it equals to 45 degrees plus angle C. So let's write it down. AA1 over sine angle C plus 45 degrees. So you might find that if we denote this as 1 and this is 2, if we get the if we calculate maybe 1 over 2, that is A1S over sine A1 sine angle 1 over A1R over sine angle 2 equals to AA1 over sine angle B plus 45 degrees over AA1 over sine angle C plus 45 degrees, right? So what can we get from this? If we simplify it, we can get sine angle 2 over sine angle 1, it equals to sine angle C plus 45 degrees over sine angle B plus 45 degrees. So we can also convert it, like make it like this. If we change some of the numbers, it's like this: sine angle 1 over sine angle 2 equals to, here is the letter B, here is the letter C, right? So since we get this, what can we get after that? Let's copy the diagram here. Let's copy it. So we place it here. If we denote, let me change color. If we denote angle AB B1 as maybe no, we have to do it in clockwise not anti-clockwise. So oh no, angle ACC1 as angle 3 and angle BCC1 as angle 4. So what can we have after that? In the same way, similar to this, to the thing above, we can get sine angle 3 over sine angle 4. It equals to maybe it's after calculating, actually it equals to sine angle A plus 45 degrees over sine angle B plus 45 degrees, and then denote angle CBB1 as angle 5, and denote angle ABB1 as angle 6. What can we have after that? That is sine angle 5 over sine angle 6. It equals to sine angle C plus 45 degrees, right? And here is sine angle A plus 45 degrees. So if here it is, how can we denote it? If we get multiply these three things, here, here, and here, what can we get? Let me use a purple pen. Sine angle 1 over sine angle 2 times sine angle 3 over sine angle 4 times sine angle 5 over sine angle 6. Actually, we can easily find that it equals to 1. And then, according to the converse of Seva's theorem, we know that, we finally proved that AA1, BB1, CC1 meet at one point. And that's the end of the proof. So thank you for watching.